Welcome to Kinematics Part 5, Full Metal Physics. All the equations you'll need to first year university. You'll only be adding one more equation next year, that of circular acceleration. Apart from that, this is the basket of motion equations that you'll need. You need to be able to use these three additional equations and rearrange them to solve for any variable present, not plug in the numbers and find the letter left over. You need to recognize that accelerated situations cannot use the formula v = d/t. You need to be able to distinguish between initial speed and final speed, which are indicating that an acceleration is present, and v, when it has no subscripts, indicates that there is a constant velocity and no acceleration. Recognize that if we write v is equal to constant, meaning it's not changing, this implies acceleration is 0 and that there's no longer a vi or a vf, just a v. And v:average is yet again a different idea. Okay? And advanced, I want you to be able to prove the two equations at the top of the screen, but that is advanced. It is not required for the most part. So let's take a look at where we start. On the far right of the screen, you see v is delta d/t, a is delta v/t, and d equals v:average_t. The delta means difference. Now here's where I have problems with a lot of textbooks and a lot of well-meaning teachers. There are three equations on the screen. On the right, on the left, those are the expansions of the equations. A equals delta v/t is vf minus vi/t. What is an average? V bar or v:average_t, either way you want to write it, is add up two numbers and divide by 2. Dividing by 2 is the same as multiplying by half. What you are going to find is the preference in physics is to write a half in front instead of creating a giant fraction and putting 2 on the bottom. So get used to division by 2 is leading with a 1/2. It occurs a lot. You need to have a little faith in yourself. The three equations on the right are the same things that I wrote on the left. You trust yourself to do the expansion. Don't write the expansions down like they are something brand new you need to learn, because it makes the work bigger than it really is. We started off with some basic distance time plots where we could have done them as labs, but COVID spoke otherwise. So I've created some pretend data here. An object is moving very uniformly in distance, marching along over 8 seconds. It covers 200 meters. We can take the slope anywhere along here because it's constant. I would take the largest slope you could. Why didn't I do that here? Because I'm trying to illustrate the slope idea, and if I filled the entire screen with a slope, it would block a lot of the reading. So our delta d/delta t, formally written out, gives us 17 meters a second. When was this object moving 17 meters a second? Consistently throughout the entire problem, it was moving at 17 meters a second from the graph. Okay? It doesn't matter. Speed is constant. This slope is not changing. Now if we look over here, why have I graphed the speed at 20 meters a second? Because these two graphs I did on a spreadsheet. This was calculated on the spreadsheet. This slope here, I've crudely attempted to read off the screen. So I got 17, not 20. That is normal. You don't freak and go, I was wrong. So if a bunch of you were using the same data and computing the slope, it's going to be between 15 and 25 if you're reading off a graph. Don't expect it's going to be as good as from a spreadsheet. Now, if we're correct, since v is d/t, we can also write d is v times t. And if we take this 20 meters a second that I calculated on the spreadsheet, we multiply it by 8 seconds, we get 160 meters. So according to this graph, an object traveling at 20 meters a second for 8 seconds traveled a total of 160 meters. And lo and behold, look at what we're seeing here. There it is. It matched. Okay? So the slope of a distance time graph will create the speed time graph. Speed times time can be interpreted as the area of this shape. Time would be the length and speed would be the width. So we can have areas that are not necessarily square meters. They're mathematical areas and have different units. So we can interpret the area under a speed time graph gives you the total distance covered. So this is the graphical interpretation of these single equation of motion. Now what happens if acceleration is present? I plotted a parabola here. This object is gaining speed, so we need to take the slope many times. I'm showing you the slope between 10 and 11 seconds. So on the spreadsheet, I just had it do a delta D over delta T for every single pair of points, and this is the data that came out. And it shows us a growing speed. Now we don't have a zero acceleration. We can take the slope of this slope and find the rate of change of the rate of change. So this is distance, this is the rate of change of distance, and this is the rate of change of speed. Okay, so we now have acceleration. So the slopes will lead us from distance to speed to acceleration. Forget about acceleration for now. Can we use the same technique of multiplying speed times time to go back to distance? Yes, except the speed is changing. Now I cover this in accelerated motion number 4. I do the same thing in a different way. Let's look at the area under this line. It's a triangle. A triangle with base of 12.5 seconds in this case, and a height of 115 meters per second. Okay, I got that from my spreadsheet. So how do we do the area of a triangle? 1/2 base times height. But in this case, it's 1/2 time times speed. So it has a mathematical meaning now, not an actual area of a floor. And when we put this all together, we will get 718 meters. And on my graph, if I go into my spreadsheet, the maximum point was 720 meters directly off the spreadsheet. Look how close it was. Okay, so we can take the area under a speed time graph, regardless of its shape. The area formula that you learned in math class will work to get you distance. You can use a triangle. Now, are we doing any other shapes? Fortunately, no, only rectangles and triangles. So here's a case where the object doesn't start from rest. The velocity begins at 50. And you notice, because it has a starting speed, the curve is distinctly more gradual than before. Okay, so I started at 50 meters a second and I added 10 meters a second for a time period of 12. So it's a very rapid acceleration. This is gaining at 10 meters per second every second. That's the same as falling. So this plot could be an object falling on Earth. So how do we calculate the area under this line? We're going to have to break it into two pieces. So what we do is break it into a rectangular area and a triangular area. The gray box would be the area as if this thing stayed at 50 meters a second for the entire run. The triangle is the area of extra distance covered. Remember, talking about the total area under there because you're accelerating. So you can easily get the area of this shape. The area of the rectangle is length times width, which is initial speed here times time. So the distance covered in this area is vit, which makes sense. The area of the triangular shape starts at vi and goes to vf. So the 1/2 base times height becomes 1/2 vf minus vit. So we wind up with the total area under the curve is the addition of these. So this example, the square area multiplies out to 600 meters, and the triangular area, when we carry it out, comes out to 720 meters. We add these two up. Sigma means the sum. We get a total area under this shape of 1,320 meters. Doesn't have area of meters squared. It is the area is speed times time here. And if you look, that is complete agreement with this number from there. So getting the area under a speed time graph is easy. It's either a rectangle, a triangle, or a combination of two. Now we just did a specific example. I don't want to do a specific example. I want to look at it without numbers, with letters only. So if this is a speed time graph showing velocity going from some starting speed like 30 and it increases to 50, we're not going to put in numbers. We're going to keep it as algebra only. So what's going to happen now is we will get a general purpose formula. And the formula is going to give us the area under this whole shape. Well, just like before, we're going to have a triangular area above and a rectangular area below. And combining these two areas mathematically will give us a formula. Nothing happened. There is the area of the rectangle, and the area of the triangle didn't animate. It just stuck there. So here's what happens. If we want to add up the distance covered in the area here plus the distance covered in the area that's triangular, we get vit plus 1/2 base times height, and we get a formula of motion that's combining constant speed times time and the increase in speed by time. Now this is just grade 9 rearranging and gathering terms, and by the time we're done, hey, wait a minute, 1/2 vi plus vf. You can convince yourself of this, that this is why that intuitive formula d equals vₐ works. This is the proof of it. Do you need to learn this proof? No, but you're going to need to know this kind of technique by university. So I would strongly encourage you, for your own sake, to start learning how these proofs work. But I will never ask you to prove this derivation. And I know of no teachers in high school. I've checked out about a dozen high schools, and I have yet to see any teacher within about 100 kilometers of this board asking students to derive the equations. So you're pretty safe if you ignore the derivation. But I would strongly encourage you to learn how to do derivations. What this shows you now, though, is why we like algebra. Because algebra allows you to construct new formulas. If you put in numbers, you're only solving for one example. D equals vₐ is one of the most neglected formulas. It's really powerful, and you can do a lot in your head with it. So I really want you to stick with this one. It is ignored by a lot of teachers. It became one of my favorites because, as you've seen in class, I'm sloppy with my math. I make a lot of small, trivial mistakes. And this is from a guy who spent 7 years at university studying physics beyond high school. I'm still sloppy with math. I need in my head double checks to catch my silly little errors I make. So here's an example. A car changes speed from 20 to 40 meters a second in 10 seconds. What distance does it cover? Well, a typical solution would be calculate acceleration, then you would put it into either vf² minus vᵢ² equals 2ad equation and get 300 meters, or you'd put it in this equation and get 300 meters. But my technique would go, oh, 20 to 40, that's an average speed of 30. 30 for 10 seconds is 300. And that's why this equation is a real rock solid one in your pocket. And that is how I am able to look at your long solution using technique 2 or 3, and I can look at it and go, you're wrong, the answer's 300, and you think I solved a quadratic in my head. I didn't. I used this technique to go right around it. So it's a great in-your-head double check. Now I'm going to show you how we can combine formulas to come up with a new one. What we did with the triangle and the rectangle is just add them up. Total up 2 different formulas. But now we want to substitute one formula in another. And you have done this in math class. If a teacher says, I want you to take y equals 3x plus 4 and y equals 2x and find me the solution for the 2 of them at once. So I'm going to take a formula from grade 9 electricity. Power is energy over time. Energy, though, is highly variable, like it covers all forms of energy. If you're in electricity class, though, you may have learned that voltage is defined as the energy per quantity of electric charge, or energy joules per coulomb. If we rearrange this, electrical energy can be written as the voltage times the charge. You may or may not have done this in grade 9 electricity. So this would allow us to take the E out of the power equation and substitute this in place. And we get this. All of a sudden, instead of having a general purpose power formula, we now have a power formula specifically about electricity. With a slight more rearrangement, you may have learned that quantity over time in electricity is current, and that is V times I. And what this has done now is created a formula. Power equals voltage times current. Power equals VI. And why is that important? Because nobody has an energy meter. They don't exist. Nobody has a joule meter. But you can go down to Canadian Tire and buy a voltmeter and a current meter, and you can instantly determine the watts in a circuit. Every device out there usually prints the voltage and the current in the device. So instead of getting energy, which is never stated for an electrical apparatus, you use other quantities. So this is how these formulas are invented in a sense. They're logical mathematical outcomes of playing with your existing formulas. So let's take this formula. Average velocity times time. And let's knock one of these letters out. Which one are we going to knock out? Well, in fact, all 3 can be knocked out and replaced. All 4, in fact, if you want. Every letter on screen can be replaced by a different expression. Let's target the vf. If I take acceleration, notice it's got a vf in it. So could I rearrange the acceleration formula to solve for vf and punch it out of the formula on the top of the screen? Yes. So we're going to substitute the lower equation into that one above so we can chase the vf away. Now what does that look like? Well, if I rearrange the acceleration formula for vf, I get vf equals vi plus at. That means the vf in that equation above, I can replace it with vi plus at. And you might go, well, that's bigger than before. Why? How would that help? It won't be bigger in a moment. If you gather all your terms, you wind up with this formula. D equals vit plus a half to vit plus 1/2 at squared. And why is that important? Because all of a sudden now, if you weren't given final speed, you found a way around it. You've now got an equation that no longer has final speed in it. And that's important because you might not have it in the problem. So each of these new derivations allow you to use different measurements for a calculation. So you're like, oh, I'm missing t. I wonder what formula doesn't have t. I'm missing vf. Hey, this formula doesn't have vf in it. It's the way you get around your missing variables by having a new relationship. Okay, so let's take a look at what this formula means. It's not a new formula, really. What you're looking at is this is saying, hey, this is the distance you cover because you were originally traveling at a constant speed, vit. And then you stepped on your gas pedal. And all of a sudden, you started adding more and more and more distance because you're accelerating. You need to understand that these two terms now have a real-world meaning. The blue box is saying, this is the distance I would be covering if I just stayed on cruise control. And the yellowish, remember I'm colorblind, box is like, oh, you just had to go ahead and step on the gas pedal, didn't you? Now look at it. We're moving faster and faster and faster because you stepped on the gas pedal. Now, what if we could knock time out of the equation? Could we rearrange it to smack out time? Let's see. If I do this and I go, I want time gone. And there's my formula again for the average speed, and I look at that delta t and go, I don't have time, I broke my watch. Could I now rearrange the upper equation to solve for time and chase time out of the formula? Yes. Now you could pause and try it yourself right now to make yourself feel as smart as I know you are. But what happens in this one? Hello, animate. Come on, there we go. When I rearrange the acceleration formula, I get delta t is this expression here. So I took out that pleasant little delta t and I replaced it with this math. It's gotten even more complicated. But time is gone now. We're going to have an equation that doesn't require us to know time. So I'm going to rearrange it a little bit. This A is lonely over here. I can group them way out front over here. And then we got this mess. And your first reaction is like, oh, do I have to expand that? You've done it in math class. It's the same as x plus y times x minus y. You've carried out that polynomial before, right? That expansion. It's not the quadratic because the second term isn't x plus y, it's x minus y. And it will cancel. You can do it yourself if you want, but it's going to cancel out to vf² minus vi², and lo and behold, there's our formula that has no reference at all to time. That's how these formulas came about. And once again, I do not expect you to be able to produce the proof for me, but this is a technique that is going to be desperately needed by first-year university. So I would encourage you to learn derivations while you're mooching off your parents for free and not paying $5,000 a semester to screw up derivations. Learn them when they're free and easy before you hit university, then you have more time for irresponsible behavior. Okay, now this is where this entire suite of equations came from. You can go vomit, forget about the proofs, and just have this basket of equations and the layout for a solution. You don't need the proofs to get really great marks in this course. The proofs are needed for the future. Okay? So let's try one example. A car goes from 11 meters a second to 35 meters a second in 8 seconds. how far does it travel in this time? Well, we list our variables, noticing that A is unc, it's unknown, and this is going to really limit our choices. We want to solve for distance, and we have everything but acceleration. We cannot use v=d/t. We cannot use that because this is not a constant speed problem. We cannot use these three equations because they all contain that unknown value of A. So out of the 5 equations, 4 of them get disqualified. This leaves us with my personal favorite, d = v'average_t. So if I put in my numbers for this one, I get 184 meters using that little formula that has saved my life on many occasions. What if you didn't notice that? Because for some reason, that really helpful equation, just students don't cotton to it too much. I have to spend an unbelievable time getting you to add that to your repertoire. It's just a quirky little thing. So some of you might do this. You might not spot the shortcut, and so you decide to tackle computing the acceleration first. And once you compute the acceleration of 3 meters per second squared, you can use either the time-independent equation or the quadratic one to get exactly the same answer. Now tell me, what would you prefer to do? That's why you really want to watch when you can use this v'average_t. But in the future, you might get a teacher that says, tell me how far it traveled using the quadratic equation. Right? You might have to check with your local teacher if they really want you to suffer. And if they want you to suffer, they're going to want you to do it this way. If they're nice like me, they're going to want you to be as lazy as possible and spot the shortcut. Let's look at example 2, a rocket sled. We're going to do lots of those. At 200 meters a second. By the way, can your car go 200 meters a second? If you can't answer that, you're not doing physics. It comes to a halt in only 10 meters. Would you like to be in a vehicle that is going 200 meters a second and it stops in 10 meters? That's only the length of a car. Do you think you spilled your drink? Let's find out. We're going to compute the acceleration of the rocket sled. So here are our variables. 10 meters, 200 meters a second, and the word halt means it stopped. We want the acceleration, and time is unc. We don't know the time. So that lack of time is a giveaway to use the only single equation that doesn't have time in it. There's your giveaway. So we rearrange. At table 1, we have the rearrangement of the equation. Table 2, we substitute in our values. Table 3, we square the top, we arrange it, and table 4 at the end, 20 meters per second squared. Okay? So 20 meters per second squared, that's a 2g halt. Okay? Now, do you have a problem with my solution? Do you believe what I just wrote? Okay? Send me an email if you think I just did that correctly. Example 3. A rock falls past a window. When it passes the window, it was traveling at 80 meters a second. 5 seconds later, the sound of it hitting the ground is heard. How high is the window? Now, this is my example of a stupid textbook problem. Where the hell on earth are you ever going to want to determine the height of the building using this method? Who the hell is able to look out a window and go like, wow, that thing went by at 80 meters a second. Time it before it hits the ground. Wait, how long was I talking? Did that hit the ground? This is a completely artificial problem. It's just like, it's a dumbass problem. Did I do a good job of imitating dumbass problems from a math textbook or science textbook? Let's see. We write our variables down. Now we got this is a vector problem because down and up are important now. But thank God, both the speed and the acceleration due to gravity are downwards. So we're not going to have to worry about direction changing. Everything's going down. We got two unknowns, distance and final speed. We were asked how high the window is. So we want distance, right? We weren't asked the final speed. So what can we use to solve for distance? Well, because I forcibly set up an incredibly artificial problem, it winds up being the easiest way to do it is with the quadratic. So I kind of had to deliberately create a problem that would force you to use this one. And all the way 525 meters. Now, if I were to ask you for the final speed, you should be able to do that without any calculations. You are gaining speed at 10 meters per second for 5 seconds. How much faster are you going at the end? You've gained 50. You've gained 50 on top of 80. You're at 130 meters a second. Okay, that d equals v average t comes in handy. Now here's another one. CN Tower is 553 meters tall to the pinnacle. What speed would you impact the ground if you fell off, and how long would the fall take? And it's a trick question, because if you were actually on the tip of the CN Tower and fell off, you'd bust through the restaurant window, land on a table, and spoil somebody's afternoon. Or delight them, depending. You know, it might be like, I promise you, if I've cheated on you, let a man fall from the sky and crash onto our table. No, so let's say you could just plunge off the top, straight for the ground below. Right into the roof of Ripley's Aquarium, and you land on a sea turtle and get charged with environmental abuse. How long is it going to take you and how fast are you going to hit the ground? Well, once again, what speed would you impact the ground? So at first, the time is a don't know, don't care. The first part of the question wanted to know your final speed. The second part is time. Once in a while, a teacher gives you a question where you might go, wait a minute, it would be easier if I did the second question first. And that's where cleverness comes in. And I can't really teach cleverness. I can only sort of pave the way to Clevertown and see if you start spotting it. So maybe some of you might want to try the time first. Would it be any easier? I don't know. So let's try this. The first part, because there's no time, the only way to get the final speed is to use the time-independent example. So we put it together, rearrange, pop in our numbers, we get 105 meters a second is the final speed. Okay? Now, what can we do to solve for time? Well, we cannot use that first equation to solve for time. A lot of you at this point go like, aha, I'm going to take v equals d over t, solve for time, and I'm going to put in that speed into the equation up there. But you can't use that equation. It's very tempting, but this isn't the only speed. The speed has changed. So that first equation, can't use it to find time. That one you can't use to find time because it doesn't even have time in it. So we're starting to run out of equations. What ones are left that would allow us to solve for the final time? Well, this one requires the quadratic. Who wants to do that? This one here doesn't need the quadratic, but it does have a flaw. It's using a calculated value. We calculated vf. So this one here would be pristine if you it doesn't have vf in it. So if you buggered up the 105, you're not passing a wrong value into this equation. This equation here would use that calculated value. But I would say under this case, you're better off doing this, because I know if I try the quadratic formula and solve for t, I'll screw it up. Almost guaranteed. So we get the time at 10.5 seconds. Now, are we correct? Now we can utilize my friend over there in the corner. And in the right corner, wearing the average bar in T, is D equals V average T. So we take 10.5 seconds fall at 10 meters per second squared. According to that, my final speed would be 105, exactly what I calculated here. And this means if my maximum speed is 105, my average speed was half of that for 10.5 seconds, which is approximately 525 meters. It worked. Now, do I expect you to follow this when you're sitting on your cell phone, sort of idly doing other stuff? No, you have to go through this a couple of times to really grab it for you, okay? So there's a rundown of those last three equations, and this is the end of Full Metal Physics!